2 weeks. Make sure you're paying attention to the requirements for that deadline. Milestone 3 will be in 3 weeks. Remember that next week's lab, which is the Digital Logic Lab, aligned very well with today's lecture, is going to be your first team lab report. So moving on through the rest of the semester, you're going to be doing team lab, report writing. Over the next 2 weeks, there will be a couple of workshops. I'll just show you really quickly on Arduino and soldering. I'll show that in just a minute. But please sign up for those if you are interested. It's first come, first serve for the registration on the Eventbrite. And then the last two things are the most important. We have midterm grades that will be posted over the next couple of weeks. We'll do it a little bit earlier for EG 1003 than some of your other courses, just so you have an update on where you are in the course. But keep in mind that this goes through Lab 4 presentations, Lab 5 reports, and only your early milestones and benchmarks for your project. So it doesn't incorporate a large portion of your grade, which comes from your semester-long design project. Remember, that's 30% of your grade, and a lot of that will be assessed at the end of the semester with the final presentation and the completion of the project. The last thing is for the RAD teams, just as a heads up, in the last week there will be a competition for the RAD teams who are interested in participating. So you'll be doing your final presentations in recitation like all of the other groups. But on Tuesday in the Makerspace event space, we'll have a run through. And then on Thursday during the lecture time in the last week of EG 1003, the RAD teams will present up here on stage for some venture funding for their projects. So, just as a heads up, we'll send out more announcements about that in just a little bit. So the advertisements for the Intro to Arduino workshop, the RSVP is this URL down here. This will be posted in an announcement later, but if you want to get a picture of it right now, that's the URL for that. And then Intro to Soldering in 2 weeks. This URL for signing up for those. So, over the last 2 weeks, you've been introduced to computer science and electrical engineering, both Professor Frankel from the CS department and Professor Knox from the electrical engineering department. So today, Professor Hal Doon will be your speaker. He's one of the people behind creating the computer engineering degree here on campus, which really bridges that gap between CS and electrical engineering. So if you can, please give Professor Hal Doon a warm welcome.
Thank you. Hello, everybody. How are you? How is your semester so far? Are you happy? If you are not, we have to work on it. I hope you are, so that you can enjoy this lecture. Hopefully you will. So let's start. My name is Haldun Hadimioğlu. I'm with the Computer Science Department. My background includes electrical engineering and computer science. So, as your professor said, I am a computer engineering person. And I will talk about digital logic, which is one of the most fundamental topics of computer engineering. And everything you see, all the pictures, everything that you will come across, including this area, yes, the brain, they are all related to digital logic soon or already. So you will see, everybody, what I mean by that. So this is our agenda, and everything that you see, yes, digital logic is involved, everybody. Digital logic is everywhere. So let's start. Everybody, it is a key component of digital evolution. No digital logic, no digital evolution. What is digital logic? It's about digital hardware. It's about logic circuits, digital circuits. And they are building blocks of digital hardware today. And every digital device has digital logic, meaning digital hardware. So no digital logic, no digital devices. So everybody, digital evolution means digital logic, and soon you will see digital logic means digital evolution. Before I finish, everybody, let's remember this and everybody keep this thing in mind so we don't have it. So we need to work on this thing as much as we can, everybody, right? So digital equality is not around, as you know. Okay, so let's take a look at digital evolution and digital logic. For example, communicating with someone, it used to be by means of human beings, mechanical, electromechanical, electronic, analog, and electronic, digital. So communicating with someone. How about listening to music, mechanical, electromechanical, analog, and then finally electronic and digital. So everybody, we are talking about digital logic today. It is electronic and of course digital, meaning not analog. How about computing? It used to be mechanical in the 19th century, and then electromechanical in the first part of the 20th century. Then it became electronic and digital, and then finally today's computers. So everybody, the difference between the middle picture and the right one is that here, this computer here is not using transistors, it is using vacuum tubes. They are big components. That's why this computer is occupying a space as large as this auditorium. It was so big. But it was the first electronic computer from 1945. But today's computers are very small because they are using transistors. Your cell phone is very small because it is using transistors. What else? How about thinking? The first computer that defeated the world chess champion was the IBM DE, defeating Kasparov there. As you see, he is not happy. He lost the match, and so he lost his title to a computer. How about the first computer beating the Jeopardy champions, the IBM Watson, and then the first computer defeating the world the world Go champion was the Google AlphaGo. So the IBM computer had custom chips used. The Google AlphaGo also used those custom chips to be able to be human beings. Also, there were custom chips with the deep clean. How about the live chips, meaning chips that are alive? So the first kind was the biochip or lab on a chip. In this case, the biochips allow you to have chemistry, biology experiments on a chip. So you can envision that in the future, chemistry students will not be going to the chemistry lab. They will be home doing the experiment at home by using these chips. We are going in that direction. But more importantly, you will not go to your doctor's office to get tested. These chips will be testing you, right? And they will be sending the result to your doctor, and your doctor will call you. How about organs on chips? People are working on them. So this is the first organ on a chip. It's a lung. The human lung is mimicked by this. The goal is that we use these organs on chips to test new drugs so that we don't use too many animals to test new drugs. You know, today we are using a lot of animals to test new drugs. It is not good. So we have to change it. And how about 3D bioprinting? So these are happening. So, for example, a small-scale human heart was 3D bioprinted in Israel, everybody, and more these will be printed so that people who need kidneys and hearts and other things will not wait for many years. They will get it right away. They will be 3D bioprinted. What else? Smart drugs, for example, swallowing this nanorobot so that it releases the drug according to doctor's prescription, monitors the situation, and then sends the results to your doctor so that everybody, you don't have side effects and you are cured quickly. All right? What else? We have shrinking objects to nanoscale. So there are lots of applications here, especially medicine, optics, and robotics. And finally, you will remember today, October 17, 2019, for the first time you hear this, and you will say, this is the first time I hear this CRISPR. So this is the tool that scientists are using to edit the human gene, everybody. And the first genetically edited twin girls born last year in China and CRISPR will be used very frequently, and you will say, okay, why did I hear CRISPR? So everybody, this is a kind of a very risky research area. It has many possibilities, especially for those who are disabled, all right, who have hereditary problems, but otherwise you can imagine that there will be a lot of issues with CRISPR, a lot of issues. Everybody, I'm getting a lot of whispering, so can you please? Thank you. So everybody, already scientists are working on human-animal hybrids. A few months ago, a Japanese scientist was given okay to experiment with monkeys, editing their DNA so that he is adding human genes, and he promised he will stop his research when the animal, monkey's brain is 30% of the human brain. Eventually it will be 40%, it will be 50%, and then we will have hybrids. Everybody, human-animal hybrids. So please think about this thing. There are many ethical issues there. All right, but let's not get so depressed. We can use CRISPR for many interesting things, like scientists develop a dual-core processor in a human cell by using CRISPR. DNA editing. Everybody? Yes, we can be depressed, and we can think about lots of ethical issues, but there are also many interesting applications. So it's a very small biotech group. And this is from your school to scientists here at Tandon working on atom thin processors on nanoscale chips, and more, for example, this one, DNA molecules, self-assembling to do computations from UC Davis, molecular computing. So everybody, these are all enabled by digital devices that have digital logic. Okay, so everybody, digital evolution, meaning digital logic has improved life. Life is better, everybody. You cannot believe how it was 30 years ago without cell phones, without the web, without the internet, nothing. So we have improved quite a lot. But formally, everybody, there is no middle person, no extra layer. So things are faster, better, cheaper. So everybody, this is critical. Can you get rid of an extra layer like a middle person so things are better for everyone? All right? But let's go back here. If you are getting rid of the middle person, some people are losing jobs. So that is a side effect, everybody. So some people are not with jobs. But there are also new opportunities. Impossible concepts become possible, everybody. And so digital evolution, propelled by digital logic, is coming up with new concepts and systems. They in turn increase the speed of digital evolution, which in turn leads to more new concepts and systems. So this is a vicious cycle, right? So they need each other. So everybody, here I'm holding a graphics processor chip, a GPU chip, with more than 3 billion transistors. So this is 12 years old. So today's NVIDIA GPUs have 20 billion transistors in the same area. 20 billion transistors. And there are chips with 100 billion transistors. And we will have more. So these transistors will be molecular size, and then who knows, you will determine what is after transistors. You will determine that. Okay. So everybody, nanotechnology will be also critical for digital logic. Nanotechnology will help us here on Earth and also in space. We need it for both, everybody. On Earth, we need to deal with the environmental issues and population. We will have cities with 400 million people, everybody. Yeah. So they are planning for these cities. And sustainability on Earth and in space, of course, everybody, lots of things during the travel and also living in the space. So nanotechnology will be needed, So nanotechnology needs visual logic, and visual logic needs nanotechnology. So this chip is benefiting from nanotechnology, and soon everybody you will have maybe molecular computers that will be behaving quite differently. How about AI and machine learning, the latest hot area? Everybody, nanotechnology through AI, artificial intelligence and machine learning, and visual logic is needed for this to solve problems, to do work for us. So eventually they will be as good as we are, these AI machine learning systems. So everybody, with AI and machine learning, we will be removing extra layers, means persons, and also we may remove the software layer so that your artificial intelligence system or machine learning system uses only hardware to do the computations, no software layer. So anyway, this is happening now. This is a new trend, and especially computer science students, watch out. So the software layer is removed little by using these reconfigurable chips, FPGA chips. So they are removing the software layer. So you have your video game. To play the game, you need software, right? But what if you play the game without software, but just hardware? It's much faster. So this is happening, and so everybody, you may be hearing more about FPGA chips in the future. Another thing, especially for computer science students, is that we are going in the direction of graphical programming. And one example of graphical languages is LabVIEW. They are learning, or they have learned, this week you are learning LabVIEW. LabVIEW is a graphical language. So these languages may be replacing Python, C, C++, Java, and already Microsoft Azure is doing this, and programmers are citizen developers. So Microsoft is not calling programmers anymore. So if you do a search as programmers on the Microsoft website, you will not come across with this, but citizen developers doing graphical programming, right? And eventually, in about 10 years or so, machines will be developing applications. Right now, human beings, you are developing applications, but eventually machines will be developing applications. So digital logic is then the first step to design chips like the one that I've been showing you, the GPU chip that you need for graphics and also high-speed computations. So everybody, this chip has 50 billion transistors, and this NVIDIA GPU has 21 billion transistors, and your DRAM chips have even more transistors. So all of them need digital logic. What else? With digital logic, everybody, you are on your way to design computers and computer boards. So here is a board with a couple of interesting chips. They are from Intel. And so Intel microprocessors have typically 8 to 10 billion transistors. So everybody, we simply say board, but you know it as the motherboard. So in general, they are boards. And computers like this one, everybody, this is the fastest computer in the world from IBM with more than 2 million cores. How can you program this computer with more than 2 million cores? All right? And look at the size of the RAM space, 11 petabytes of RAM there. So everybody, the Summit computer is one of 17 computers that are faster than the human brain. So everybody, we are going in that direction. Machines are becoming smarter and faster than human beings. So the speculated speed of the human brain is 200 petaflops. Sorry, 220 petaflops. The human brain speed. 20 petaflops, but this is 200 petaflops. What is petaflop? For 10 to the 15. And flops means real number of calculations a second. So this is doing more than 200 times 10 to the 15 real number of calculations a second. Am I losing connection? Maybe I should walk away from here. Okay. So the human brain speed, 20 petaflops. And today's computers, there are 17 of them faster than this, but eventually your laptop will be faster than your brain. Your cell phone will be faster than your brain. So these are the others that are faster than the human brain. And here is the list from top 500. So if you do a Google search, everybody will get this list. The top 10 supercomputers in the world, the fastest computers in the world. Everybody look at the speeds. Top speeds from 200 to 26 petaflops there. And they cost about $100 million to $200 million. Very expensive. What else can you do with digital logic? It is the first step to design embedded systems like robots and cell phones and cars. They are all embedded systems, meaning that you have a tiny controller controlling the larger system. They are embedded in the larger system. Your car has around 40, 50 microprocessors controlling the car. Your cell phone has 4, 5, 6, 7, 8 cores, and your robot is useless without a controller, and that controller is a tiny computer with a board on. So these are everybody possible with digital logic. So smart watches, yes, and autonomous cars. Soon we will be working on these, and they will be all around us. Maybe it will be better for us with autonomous cars. Digital logic is also a starting point for nanotechnology. Remember, nanotechnology needs digital logic, right? So molecular machines and other things that you see there. So everybody, because today's digital hardware uses transistors and they are nanosized. Today's transistors are nanosized. So the sky is the limit. Everybody look at the window you will see here. So the sky is the limit for applications. This one. How about this? Robot hands for people who cannot walk. All right, the sky is the limit. Okay. So these are possible with digital logic. Okay. So let's take a break. Questions, comments, ideas. Professor, give us a minute. Okay. Why don't you do this, everybody? Look to your right side, look to your left side, and see if there is anyone who needs your tapping on the shoulder. Question? How do we compare vacuum tubes to transistors? Are they the same?
Everybody quiet down. I have a question. What's your question?
Earlier you mentioned vacuum tubes. How do those compare to transistors in the sense, like how do they work?
Vacuum tubes were developed in the late 19th century. They are large, so you cannot have 100 helium vacuum tubes for a computer or a chip. They are big, they consume a lot of power, but they are electronic. And there is a tube with no air inside, and there are 2 terminals. And when we apply a high voltage, electrical current will flow from one terminal to the other inside the tube. So we say the tube has been turned on. If there is no current, the tube has been turned off. So it is like a switch, and it's like a transistor that is turned on and off. But transistors are much smaller, faster, they don't get hot like vacuum tubes, more reliable. So this is the progression of our evolution. Mechanical devices, then electromechanical devices, then electronic devices. The first electronic device was the vacuum tube, and then transistors. Okay? All right, we are okay with this? Yes.
Earlier you said that programming is becoming a little obsolete and we're moving more towards graphical programming with things like LabVIEW. So would you say that computer science kind of like as a degree is also becoming obsolete, or how's it adapting? Do we need programmers anymore?
All right, everybody, we are removing the software layer, but we still need programming. Eventually, computers will be doing programming, yes, because our programs are getting so complex. Even a team of developers is not able to come up with a secure and correct piece of software. So we will rely on machines more and more with the help of AI and machine learning. So right now, machines cannot do programming, but we are working on artificial intelligence systems, so eventually they will be doing programming. Because software will become so complex, human beings will not be able to tackle. Then what will happen to computer science? My answer is this: nothing is permanent. 20, 30 years ago, it was electrical engineering that was the hottest area. Now it is computer science. So the next hot area is biology, chemistry, chemical engineering. But we will still need programmers. So my comment, my advice for computer science students, don't say that all I need to know is programming. Make sure you learn more than just programming. Life is not permanent. Yes.
All right, hello. So my question is, because like I know that you mentioned that 30 years ago we had other technology which was a lot bigger, clunkier. Now we could have done it. It's faster, and I also know that like there's like this rule where like the processing gets like twice as fast every year because the transistors are getting smaller and smaller. What's after the transistors? Because we're reaching the limit.
Well, you touched upon a good topic. I have a lot of slides on that. So, what is life after transistors? Biology, chemistry. We may be using protein molecules instead of transistors. We may be using DNA molecules instead of transistors. So that's why I've been calling molecular computing. Or human cells, or cells doing computations. Scientists have already developed cells, biological cells that are doing computation. Right? So the next hot area is biology, chemistry, chemical engineering.
So necessarily, does CRISPR use nanotechnology, or does it use data logic? Within like, because I know CRISPR changes the code of DNA and RNA. So like,
the CRISPR platform has hardware and software. Hardware means there is digital logic there. Software means you have microprocessors that are running the software, which means you have digital logic used to implement your microprocessors. So CRISPR is possible because of digital evolution. We are able to play with very tiny molecules. We can edit these DNA molecules. It was not possible 20, 30 years ago, but we have nanotechnology propelled by, of course, digital evolution. So digital logic propelled digital evolution, which led to nanotechnology, and nanotechnology is helping digital logic because we can pack more transistors on chips. So you have more capability on chips, so they can do more. Right? Your microprocessors can do more. So there is a cycle back, helping us. Right? Yes?
Okay, so do you really think that it's going to be more biological based rather than like quantum computing in the future?
Everybody you heard the question, right? So will it be biological or quantum? So here's one piece of advice that I would like you to remember. Do not trust experts. They may be wrong. So I may be wrong. All right? So it needs quantum computing first, and then biological or chemical computing. But right now, we have more headway with these biological chemical systems than quantum. Right? The quantum side is still in its infancy. but they may pick up the pace and they may be introduced before biological computers are introduced. Right? Who is next? Where is the microphone? Somebody has the microphone. So she has, and then we will be done. Yes.
So like a couple slides ago, there was this one concept that really piqued my attention, which was DNAs, like self-assembling DNAs, DNA Lego, something like that. And I wanted to ask you, do you think there will come a point where we could just sort of like program the electromagnetic field maybe and sync it to our brain and let like whatever we start to think to like start like sort of like self-assemble into that shape? Or are we not quite there yet?
We are not there yet. It is possible. Nothing is impossible. Nothing is impossible, but everybody, already scientists have developed ways of having wireless communication between your brain and the outside world. All right? And then eventually this communication will be done without electronics but with biological systems. So wireless communication without electronics, when we have it, the sky is the limit. Yes.
Do you believe that Moore's law will continue indefinitely?
No, Moore's law will not continue indefinitely. That's why I was suggesting that we may need chemical biological help, like DNA molecules, protein molecules. But when will this happen? We don't know. You will determine that. In 10 years, maybe a bit too ambitious. In 20 years, maybe possible.
Last one.
Okay.
Do you think ethics will be a barrier in this field?
Which one is a barrier?
Ethics. So like the continuation
So
of...
everybody, please take a course on ethics before you graduate. Every day you will be dealing with ethical issues because every day you will play with molecules. Today we are playing with transistors. Today's transistors have about 10,000 to 20,000 molecules. But you will be playing with molecules. So every day you will be dealing with ethical issues. So please take a course on ethics. All right? That will be a tough thing every day. So I will give you examples so you will see why it is important. All right? Everybody, you cannot believe, but this place is in New York. New Yorkers. What is the name of this place? Yes, New York is not all skyscrapers and buildings. So when we have a long weekend, we will go there. Where is it? No one is raising a hand. Yes. Not the airport. Yes.
Staten Island.
Not Staten Island. Yes. Not Long Island, this is New York City. Somebody is saying, not Battery Park. No.
Rikers.
No. All right, you think about it and let your professor know. Yes. No, not Manhattan. All right, let's start. Let's continue. So this is about your lab next week. So let's be serious a bit. So the second slide said digital logic is about digital circuits, right? Meaning digital hardware. So digital logic solves problems by using logic. That's why we have the word logic. Right? The logic that you have there is implemented by logic circuits or digital circuits. Sorry, I'm rushing. So here, this digital circuit has 4 inputs and 1 output and solving a problem logically. Right? But today, we are using gates and flip-flops in these digital circuits. Right? So on the left side, you see gates, and you will be using them next week. AND gates, OR gates, and NOT gates. We use flip-flops to store bits, ones, and zeros. Everybody, so this output gives you the bits stored. This output gives you the bits stored. So one flip-flop stores one bit. Everybody, combination circuits have only gates. So next week you will be developing a combination circuit. So let's see, when your professor asks, what is the name of digital circuit with only gates? Let's see how many of you will answer without looking at their notes of this presentation. How many of you will remember? Digital circuits with only gates. But most real-life circuits are sequential because we have to store and then use later on. So everybody, real-life circuits have also flip-flops. Okay? So can we implement applications without software? Meaning, can we implement applications with only gates and flip-flops without using software? Yes. Today this is happening with FPGA chips. And this is a new trend, it is accelerating, and they are all over everybody. So make sure that you know something about these FPGA chips or reconfigurable chips. So still you do programming, but when you program, the next thing is compiling your program not to software but to hardware. So when you compile, you end up with gates and flip-flops. When you compile, you end up with gates and flip-flops, no software. Yes? Is it possible to... Machine learning programs are perfect for FPGA chips. Microprocessors are not good at machine learning. Graphics processor chips, GPUs are good at machine learning, and FPGA chips are good at machine learning. But here you have software. If you are using a GPU, there is software. We are getting rid of software with the FPGA chips, so they are faster. If you are going to have an interview with financial institutions in Manhattan, they may ask you this question. What do you know about FPGA chips? They are using FPGA chips, everybody, to run their applications. Let's continue. So everybody, a digital circuit receives digital signals and generates digital signals. So in the lab next week, you will be getting inputs that are digital signals, and you will generate outputs based on the processing, right? A digital signal takes on a finite number of discrete values. Today it is 2 different values. But tomorrow, when you have DNA molecules used instead of transistors, you will have 4 values. Because we have 4 types of DNA molecules. What are they? A, C, G, T. So when we have DNA computations, this will be 4 different values. But today it is 2, 0 and 1. All right? So if you have just 0 and 1, you have binary numbers, meaning they have only bits, binary digits. So you have to use binary numbers, not decimal numbers. Anyway, so that's why you need flip-flops, where you store a bit on a flip-flop. Right? And so here's your digital signal with respect to time. So your inputs are receiving digital signals and generating digital signals. How about a byte? What is a byte? You have a 4 gigabyte memory. So what is the meaning of byte? 8 gigabytes, 16 gigabytes, 32 gigabytes. What is a byte? Yes. 8 bits for a byte, everybody. So if you have 4 gigabytes, it means you have 4 times 8, 32 gigabits. What is giga? Giga is billion. So you have 32 billion bits on your computer memory. Okay. All right. So everybody, your digital circuit needs gates and flip-flops. And next week you will be using gates, so let's take a look at that. A gate is an electronic circuit. Today, it's an electronic circuit that implements a logic operation. Tomorrow, it can be chemical or biological. So everybody, your logic operation indicates what happens for your output given the inputs. So you have one output from your gate and multiple inputs. depending on the gate. So let's take a look at your gates that you will be using next week. All gates output a 1, everybody, when one input is 1. Just one input is enough to raise the output to 1. How about AND gates? They output a 1 if all the inputs are 1. Just one input is enough. Here you have all the inputs that must be 1. Your NOT gate outputs the opposite of the input. So if the input is 1, the output is 0. If it is 0, the output is 1. So today's microprocessors, GPUs, all of them are using these gates so that we can run software, we can have applications. Your gates can have, OR gates and AND gates can have multiple, meaning more than 2 inputs. 3 inputs, 4 inputs, 5 inputs, etc. Right? So I believe next week you will be using 2 input gates, 2 input OR gates and 2 input AND gates, if I'm not wrong. And NOT gates too. So let's develop this circuit that is similar to your circuit next week. Let's develop a car seat alarm circuit. So you have 4 inputs. E for engine. If the engine is turned on, E is 1. This is the driver's seat belt. If it is fastened, this is 1. This is the passenger seat belt. So if it is fastened, this is 1. This is the back row. All right? So we will sound the alarm. Alarm is 1. If the engine is on, and so we are developing the circuit simultaneously. If the engine is on, and we are thinking logically, everybody, so it is easy to get the circuit, and the driver's seat belt is not fastened. DSP is 0, so you invert it so that this is 1. Or we have an OR gate, the passenger seat belt is not fastened, or the back row seat belt is not fastened. All right? So here's your combination circuit with 5 gates, everybody, and here's the expression for this circuit. So this is a logic circuit, a combination circuit, everybody, and when you take the digital logic course, everybody, right away, starting week 3, you will be developing circuits like this. Okay? Is this sophisticated, intelligent? No, everybody. For example, you may turn on the engine but leave the car because you want to get something from home. So the alarm will be sounding. It shouldn't sound, right? You turn on the engine, you went home to pick up something, but the alarm is sounding. So you need more input so that it is more sophisticated. What do you need? For example, what extra input can you have there so that it is better? Yes?
A pressure sensor that has a threshold.
So yes, this is sounding. The driver is not has not fastened the seat belt, so this is 0. But you can take if the driver is in the car, meaning a pressure sensor, so that you see if the driver is sitting down. Right? So you need one more input here to check if the driver is sitting down. Okay? So more input will make it more sophisticated. Okay. So everybody, today's logic circuits are implemented by gates, and today gates are implemented by transistors. So today's logic circuits are implemented by transistors. Today by transistors. Why do we need the transistors? We are using them as switches, on-off switches. So your classmate asked you about vacuum tubes. Vacuum tubes are turned on and off. Transistors are turned on and off. Close the switch, open the switch. So you can do it with transistors, you can do it with vacuum tubes. But we are doing it with protein molecules, for example. They are polarized one way, so they are 0. They are polarized the other way, so they are 1. So they have 2 different values. All right? So these are happening at research labs, and there will be more research. So protein molecules can be used as switches to implement gates that implement your digital devices. Okay. So today we need electronics for digital logic, everybody, because we are getting electronic switches, transistors, but tomorrow it will be different. Of course, there is a question mark, how about quantum computing? So it will be different matter, so we'll see which one will be implemented first, meaning which one will be more practical. Cheap, for example. So eventually, everybody, your cell phone will be more intelligent than you are. Yep. Because you will be making that. You will be making systems that will be more intelligent than you are. All of them. Yes. So with digital logic, you can do these, everybody. Digital temperature controller, clock, car seat alarm, we just did it, etc. And you can do some other more interesting games, like our students are implementing a game by using FPGA chips, so the game is played by hardware, there is no software, when these concepts are discussed. So the course is a 4-credit course with 3 lecture hours a week and 3 lab hours. So students develop a game chip, they use a program, they write a program in a hardware description language that describes the circuit. So if you write the program, it means you design the hardware. The tool conversely programmed to gates and flip-flops, you are done with your implementation. So we don't fabricate the chip, we just use FPGA chips. We program the FPGA chips to emulate the game chip everybody. So FPGA chips are used to emulate a chip, a custom chip that is for an application. So for example, you are running a video game, all right? The game is implemented by software. The software is run by your microprocessor. If you get rid of the microprocessor, the game is played by FPGA chips, so your FPGA chip is a custom chip playing your own game. So FPGA chips are faster than microprocessors, and they are as fast as GPUs. GPUs are good, but they consume a lot of electrical power, so they are not good for mobile applications. Cell phones, laptops, you need to be careful with GPUs, meaning graphics processors. So hardware plays the game, there is no software. All right? Okay. This is the new trend. Blade Runner. So everybody, let's take a look at what happened in the past to learn from the past so that we will not be making those mistakes. It is getting slightly warmer here, so let's do the same thing one more time. Look to your right, look to your left, and see if anyone needs tapping on the shoulder. Question that?
What qualifies a computer being smarter than a human? Because you would say like things like calculators and other gadgets already do like calculate things faster than we do. So is it like a computer doing something before you even think for it to do it?
So calculators are faster than our brain's calculations, definitely. Computers are also faster because they are faster than calculators. But computers are not good at AI machine learning yet. So we are working on it now. There is a lot of research and development on AI and machine learning now. So maybe in 10 years this will mature and they will be just taking over. But what is my suggestion for all of you? Everybody, don't say my field is this, I will just learn this. Try to learn as much as possible. The more you learn, the better. So be multidimensional. Multidimensional. If you say like computer science is programming, that's a wrong path. I need to learn more. Right? So everybody take a course on biology, chemistry, take a course on ethics. All right, before you graduate. All right, Derek? Did I answer your question? Okay. So what happened in the past, everybody? These 3 scientists developed the first transistor in 1947. Everybody, it took about 10 years to master the technology, so our classmate can see the vacuum tube there. Our classmate can see the vacuum tube there. All right? So we replace vacuum tubes with transistors. All right? And so today we have very small devices. So back then, in the 50s, transistors were implemented by germanium, a semiconductor, but today we are using silicon, which is another semiconductor. We need to use semiconductors so that sometimes they conduct, so they are turned on, and sometimes they don't conduct, so they are turned off. So we can use them as switches, and that means that we are using semiconductors, not conductors. If they conduct all the time, they are turned on all the time. They are not turned off, so we cannot use them as switches. Everybody, one of them is critical for digital evolution. William Shockley, he left the company and moved to Mountain View in 1955. Back then, that area was not called Silicon Valley. He just moved to Mountain View. And obviously, they got the Nobel Prize in 1956. Maybe this was the most important invention of the 20th century. Back to William Shockley. Something to remember following this lecture. William Shockley wanted to hire people for this company, but nobody wanted to work with him, for him. He was the top person about transistors in the world. Everybody knew him, but nobody wanted to work with him. Why? Steve Jobs says, hey, come work with me, and you say no. Why? The owner of Amazon calls you and says, okay, I want to hire you, and you say no. Why? There is something to remember after this lecture. You may be the top person in your area, but if people cannot talk to you, if you treat them badly, they will not work for you. So he was forced to hire 8 young people who didn't know much about him. And these 8 people changed history. These 8 people. They were really bright, everybody. So here they are. And so one of them is also important for NYU Penn, this person, soon we will talk about. But guess what? They realized in a year, oh no, we cannot work with him. Let's get out of this company, and they left the company. Right? They formed their own company called Fairchild Semiconductor, and they started working on the first chip. You see, he was the top person in the world, but he didn't realize that the future lies with chips, not with transistors. But they knew. So they went ahead, and they almost got the first chip manufactured. They were so bright. So everybody, this place in Mountain View is protected as it's a historical place, and they worked on silicon transistors rather than germanium that he was working on. And so silicon became the substance to use, and then you have Silicon Valley today, not Germanium Valley. Germanium Valley, does it sound right? No. Okay. So everybody, the first chip was manufactured by Jack Kilby, and he got his Nobel Prize in 2000, but they could have received the Nobel Prize. They lost by a few months. They were so good, everybody. He was working on this for many years. They had just a few years to work on. They almost did Jack Kilby. Robert Noyce was the patent holder for a different patent, but it was also a chip. So 3 people to remember: Robert Noyce, Eugene Kleiner, and Gordon Moore. Let's start with Eugene Kleiner. He was a Poly graduate, meaning this school. So he got his bachelor's degree in mechanical engineering here at Brooklyn Poly, and then he moved to Manhattan, and he got his master's degree from mechanical engineering at NYU Engineering. Back then, NYU had its own engineering school. NYU closed down its engineering school in 1973. And then NYU got its engineering school in 2014 back. So he has 2 degrees from NYU. How about Gordon Moore? Gordon Moore and Robert Noyce formed a company called Intel. Gordon Moore is also the person who came up with the observation known as Moore's Law in 1965. So another thing to remember following this lecture is Moore's Law. Right? So according to Moore's Law, we are doubling number of transistors on chips every 2 years. It's every 2 years, not 18 months. A lot of articles have 18 months. That is incorrect. So you will need to correct the person. It is not 18 months, but 2 years. Gordon Moore said, in 1965, when I published my paper, I wrote 2 years. So he said that. So it is 2 years. We are doubling the number of transistors. So this is because our transistors are getting smaller and smaller. They are nano-sized now. All right? So this will continue, but for how long, we don't know. We don't know. You will determine that. All right, everybody, transistors are becoming smaller because what you call the process length is getting smaller. So if you know the process length, the minimum distance between two wires on the chip, you can approximate the size of the transistor on the chip. About 3 times the process length by 5 times the process. Every year, this is getting better. So do you realize that every year I'm changing this number? So next time when I give this lecture, this will be 7. So we have already chips with 7 nanometer technology. So this is getting better. So you have more transistors on your chip. So with smaller transistors, everyone, you have faster transistors because of pure electronics and physics. Also, they consume less power, so you can have your device working such that you don't need to connect it to the outlet often. And finally, with more transistors, you have more functionality on the chip, or you have smaller devices. So this is an interesting example. In the 1990s, Intel was selling supercomputers. The top computer in the world back then used 9,000 chips to achieve 1 teraflops. But today, just one chip is enough to achieve 1 teraflops. So this supercomputer occupied an area like this auditorium. But today, it is your desktop. It is your desktop. And this trend continues. Okay. Eventually, these transistors will be so small they will not operate well. So everybody, the thinking is that carbon nanotubes will be next, carbon nanotubes. And if there is time, graphene, and then quantum or protein molecules or DNA molecules or biological cells. Biological cells during computations. All right. How about plastic computers? They can bend, so you can fold your computer like you are folding a sheet of paper. So these are work done today. The first carbon nanotube computer has been built, everybody. So we have a lot of experience with carbon nanotubes. They may be replacing transistors, silicon transistors. So everybody, let's make sure that we know the meaning of nano. It is below 100 nanometer and about 1 nanometer, about the size of complex molecules like DNA molecules. All right, when we say nanotechnology, we mean this scale. So everybody, nanotechnology will help everybody with faster, smaller chips systems. It will help mechanical engineering people, civil engineering people, electrical engineering people with smaller, faster, better devices systems. It will help chemistry, biology, and medicine because we will have smaller, faster components. So we need this for a better world, such as water creation, microreactors. Everybody, the sky is the limit. How about this? Self-healing walls. These are called programmable matter. The matter that is programmable. So imagine, especially in space, this is definitely needed in space. self-healing. You will not have to go to your tailor to get your custom-made jacket. You will buy a jacket and it will shrink to your body size. They are work done. This is not science fiction. All right, so let's go a little bit past DNA computing. I have some news for our biology students. Scientists have just developed 4 new DNA molecules. They are called P, B, Z, and S. So now we have 8 DNA molecules. So who knows? Humanized animals, they will be around us. Anyway, let's not get depressed, huh? Nanotechnology will help people with disabilities definitely, and also problems that arise with aging, like memory loss, everybody. So we will get help from nanotechnology. So these are for your curiosity, everybody. Organs on chips, and other organs are worked on. Okay, how about 3D bioprinting? Yes, these are happening also. How about 3D bioprinting of the brain? Eventually you will be working at it. So everybody, here is something you may be wondering, how come we are talking about the human body and digital logic? Here is one reason. A part bio, part electronic transistor is devised so that it doesn't need electricity to do operation, but the power given by the biological cell. The cell gives the power to this transistor. So imagine devices that are using part bio, part electronic transistors. So they can monitor 3 diseases. So it will help people with disabilities around everybody. But there will be many ethical issues, so be prepared. But let's not get depressed. I know this is a depressing slide. So to show that human body can be hacked, this is the first example of the human body getting hacked by outsiders. So the scientists planted a tiny RFID chip to his left wrist. There is an empty area in the left wrist, everybody here. And then he was able to get into his building without using his ID card. So the RFID chip was opening the door, and also he was using his mobile phone. But then he deliberately hacked this RFID chip, introduced a software virus, so the chip was not working. So we will have a lot of chips in our bodies, and they will be hacked. They will be hacked. All right, I'm going to stop. There are lots of examples here. You can think about them. FPGA chips, let's skip them. Anything interesting so that everybody you can take away with you. How about this? Brain downloads possible by the year 2050, saving the content of your brain. Eventually we will have wireless communication between you and the outside world. Ideas for you, you are welcome to use them for your own company. But let me know that you are successful. And everybody, please look at this slide. Everybody. Please look at this slide. Let's not get depressed. Let this happen, huh? All right, so I will stop at this point, everybody. I guess we are late, so we will not take questions, but I will be here. You can come up. Have a good semester, everybody. Enjoy your studies. Scientists are like this. If you want to contemplate your now we are exploring this. Always remember the atom part, when you are dealing with simple thread, that makes a lot of sense. So we have the energy, the atomic energy for good reason. So we don't go coal or wood or power, but it can be used back for heating. Did I answer your question or you have something else?
Really where your text there.
So I'll be here, if you have questions, you can ask. So I'll be here, so you can ask questions unless you are running to your class. So nanotechnology, yes.